get that. Well, I'm going to get rolling, and people can roll in as necessary. I thought this was interesting. I got an email with this in it a couple of days ago, and I thought this might be something that interests some of you. Some of you are probably going to do projects that are related to geothermal energy writ large, and so having a perspective that we probably won't get in this class of the statistics of how much is used, who uses it, what context, where in the country, etc. You already know a bit about it. We know that hydrothermal stuff is in the West, Nevada, California, Oregon, etc. This happens to be a picture of the Forge site, the U.S. EGS demonstration project and research lab, which is just getting underway, which is in Milford, Utah, about a couple of hours away from Salt Lake City, in the middle of nowhere, as you see, kind of typical Western scenery for Utah, right on the periphery of an existing hydrothermal site where it isn't hydrothermal. This is very impermeable, low permeability rock. So it is kind of like what an EGS project would be, but it happens to be in the West. So it won a competition to be the chosen one. And so I don't know what's in here. I didn't look at it, but facts and figures, and actually it's very easy reading, just because it's been presented by an illustrator and someone who knows how to pull the interesting content out of an otherwise dull and lifeless report and give you little bullets so you can scan it in not too much time. So I won't put it on the website, but you can find out where it is. It's just by searching on it. The title is 2021 U.S. Geothermal Power Production and District Heating Market Report. And that's there. Okay. So we're here this week. You are here this week. Next week, I'm out of town, so the classes are online. So just do what all your other colleagues have been doing and do the quizzes to which you had supplied answers. So one of you will get a free ride, I think. Well, not I think. One of you will get a free ride for 1 out of the 20, right? So 5.1 and 5.2 will be online from the recordings from last year. And I guess I was going to say something about this. So today, if I look back at this, I thought, patting myself on the back, that I did an exceptional job for this particular class last year. And so these are the ones that you download. And so I don't think you can do it. Well, of course you can do it online. I don't know whether you can run them at 60 speed. Probably a bit too fast if you want to get any of the content, but certainly 30 speed will run through in 3 minutes, right? And so we'll talk about the same things. I'll put up 60 speed. We'll talk about a recap from what we did last time. I'm not going to do all the handwriting today. I'm feeling lazy today. So I'm going to borrow from the material that was from last year and work through it in the revised notes that you now have for 4.2, just as a change, but you can see exactly what we went through last time. Well, this is probably normal, but the rest was all kind of handwritten and etc. So we'll go through this. So what we'll talk about today is, so far we've talked about Darcy's Law. We've seen that we can write Darcy's Law both for single fluids and for multiple fluids, and we know something about relative permeability. That's useful to us. We can put it in a more sophisticated framework. So Darcy's Law is the kind of constitutive law, or the behavioral law, and to be able to solve real problems, we actually have to put them in some kind of context. And the context we put it in to solve big problems is to have a conservation equation. And the conservation equation for the subsurface flow happens to be conservation of mass. Mass rate in, mass rate out. The difference between those equals accumulation. And we can write a partial differential equation to describe that. And then we can try some very simple solutions to that, mainly steady state, not looking at the behavior, but looking at something that is different from just a single tube, like a core sample, which is what we've done so far. So that's kind of our track for today. So I suppose I could play you that recording at normal speed and just go and get a coffee, but I won't do that. That's not what I'm inclined to do. What I'll do is instead give a little recap of what we did and then kind of move ahead. So this is what we talked about last time. So as I mentioned already, we discussed Darcy's law. If I use something that's a different color, we know that it relies on the fact when you have multiple fluids that we can kind of sequester the different fluids in a single part of the core. That doesn't really happen. They're actually all distributed amongst themselves. But the relative saturations that define, if you remember, the saturation defines the volume of that fluid 1 divided by the volume of the voids, is the proportion of the pore space which is filled up with the individual fluids. And so if you could centrifuge them down, it would look like this, and then you can describe the behavior by Darcy's law. Darcy's law usually looks like these ringed components here only: permeability, dynamic viscosity, pressure gradient. But when we deal with multiple fluids, all we do is we take each part of this core individually and we multiply it through by what we call a relative permeability. Relative permeabilities vary between 0 and 1. We can define them on a graph like this, which isn't numbered. And we said that if it's just really the cross-sectional area of flow, then we can do an X shape from corner to corner, and that would be the relative permeabilities. And if you have a particular saturation, then for that saturation, that gives you a relative permeability to the wetting fluid, which will be 100% when it's 100% water saturated, and it will give you a relative permeability to the non-wetting fluid. And those are the numbers that you would use in this. So something like 66.66 and 0.33 are for each of these values for the two different cases. We have an area which is the cross-sectional area of the entire core, or the flow area, and so that's easy for us to determine. And we talked about the reality that you couldn't get into these zones. There's some zone where you can't actually reduce the liquid water content beyond some region. We call it the irreducible saturation of water. The terminology we use is SW0 for irreducible, 0. And that means that since you can't kind of get in this region, the relative permeability curves might actually look like these steeper X curves instead of flatter, steeper, that are just barred from going into these areas. And it doesn't change things very much because this might be of the order of 10% on each side, so it changes it very slightly. And so with that, we can guess if we know what our saturations were. And I guess the other thing that we put this in context with was the idea that if we have a enthalpy versus temperature or pressure curve, that we have this dome, we have these contours coming in and out the other side. Oops. Isobaric and isothermal across it, and then off here, is that if you come in with something which is isentropic, no change in entropy in the system, then you go down here, you'd have a proportion, a saturation basically. This would be a saturation of 1, this would be a saturation of 0 in terms of water saturations. The 0 would be 100% steam, and so this would define the saturation. So this is a saturation of 65% water and 35% steam. So we know how to get that if we went into the reservoir. We always have to know exactly what the permeability is. We don't really know that very well, but we can measure it in the lab or we can measure it in the field. I don't think we defined this, but this is an important relation. It relates permeability and dynamic viscosity to hydraulic conductivity. Great. Can't work out whether he just couldn't work out to turn it off or whether he found he's in the wrong place. No problem. And density of water, density of the fluid, and gravity. So this is just an alternate way of writing it. So this is the way that petroleum engineers and geothermal engineers would write it, because we're dealing with large temperature ranges and large changes in temperatures of fluids and therefore viscosities. And this is how groundwater hydrologists would use it, who always have water at 10 degrees centigrade or 55 Fahrenheit. And this parameter of hydraulic conductivity is a property of the porous medium, but also includes the viscosity in that. And it assumes that the viscosity is of the fluid of water at 55 degrees. And so we'll use both of these as we go through this, just because this is a little bit easier. We talked about Capri models for porous media, and that was that we could dream what the behavior of the porous medium was if we knew what the pore sizes were. And if we know what the pore sizes are, we could just go through it by arranging a whole bunch of these Capri tubes for which have known transmission characteristics from the fundamental solutions. And if we do that, we get a permeability which is equal to the pore diameter squared, the porosity, and some factor. It could be 32 or 96, depending on we have Capri tubes going one way or in 3 different directions across the thing. And as we'll find out today, we can think of things in terms of Bernoulli, total hydraulic head really being the first 2 of these coefficients here. I don't know why I've got arrows through them here. Typically in groundwater flow, we're looking at changes, and the changes in velocity are quite small, but the changes in pressure and elevation can be quite large. And so we typically ignore this velocity term, and so it makes life for us much easier. But if you plot behaviors within a reservoir in terms of pressure, then you know that in a swimming pool, as you go down, the pressure increases. You know that the pressure increases according to this. But this is static. Swimming pool water is static, right? And so the fact that it's static means that this is accounting, the pressure is accounting for the internal weight of the fluid. So if you measure in the subsurface a pressure gradient which is so-called hydrostatic, which is this, then that means it's not moving. If it's above the hydrostatic, then it means it's going upwards. If it's below the hydrostatic, then it's going downwards. But on the hydrostatic, it's stagnant. If you define it in terms of, instead of pressure, in terms of head, then head at every single point within your swimming pool, from the surface, where the pressure is 0 and the elevation's 10 meters, to the base, where the elevation is 0 and the pressure is equal to 10 meters of water, this term here, then the head within the stagnant fluid is 0. The head gradient is 0. And so if the head gradient you measure is actually above this 0 gradient, then it's also flowing upwards, and if it's less than, it's going downwards. So you have to be aware of that when we deal with these things. So that's kind of where we're going. This was my handwritten stuff last time, which we won't, well, actually we'll go through. So what we'd like to do today is take it from here, realize the fact that, one, when we look at porous media, perhaps we're looking not at porous media but fractures, and that we should know something about the permeability of fractured media, because those are going to be the highly conductive features within our reservoir which supply us with the most fluid. And then we'll try and cast that permeability into a picture of how we deal with more complicated flow systems than we've dealt with. So the idea for dealing with a fracture is the same as looking at these Capri models. So we take a core, a square core in this particular case. We think of a fracture, which would be given by these horizontal lines here, or the red vertical lines. And the fractures are separated by an aperture of B, which might be of the order of a millimeter or a centimeter, not a foot, but something of that order. And the spacing between fractures is this term between individual fractures, and this might be a foot or 10 feet or 10 meters or some much larger distance. And so if we know what the fundamental equation is for flow within a single fracture, and it is that the transmission is proportional to the aperture squared. So if you double the, pardon me, if you double the aperture, you quadruple the flow velocity, which is really what permeability says. And if we put that characteristic into Darcy's law, we get an expression that says something like this. This is the cross-sectional area of flow, which is B times W, right? This times this would be this cross-sectional area of flow for single fracture. The transmission characteristics would be b squared over 12. It's a function of the viscosity and the pressure gradient. And if we include in this the number of stream tubes, number of these fractures that we'd have within a meter. So if the spacing between fractures is 1/4 of a meter, and we want to know what the flow is within a meter square section, then clearly we'd have 4 fractures, 1 over 0.25 of a meter within that. And so we can just multiply through this expression here by the number of fractures we have. This would be for 1 fracture. And if we multiply it through by the number of fractures we had, we just multiply it through by 1 over s. So this is the equation for 1 fracture. If I want to get rid of that, put it in for multiple. Then we just multiply by the number of fractures, which is this, right? And in which case we end up with an expression for, this would be the pressure gradient. This would be the area of flow, relative area of flow. And we're left, no. This would be b squared, this would be b, this would be 1 over s. I guess the bottom line is that the permeability is given by this very simple expression. And so just like the Capri model, which was porosity times d squared over 32 or 96, this is b cubed over aperture over spacing divided by 12. Not very useful in some respects in that we can't figure out exactly what the aperture is very easily. But we could rewrite this. If we rewrote this in terms of aperture, we could write that b cubed is equal to permeability times 12s. And if we cube root both sides, we could estimate a fracture aperture given by this. And so that may seem kind of a circular argument, but we can measure permeability quite easily in the field by doing pumping tests at the scale of a reservoir. We can probably measure spacing quite easily as well by looking at core or looking at along boreholes with a borehole camera. And so we can get both of these, and we might want to be able to calculate aperture. Of course, once we have aperture, we don't need it because we've already got K. But if we think that within the reservoir, something like cooling of the rock blocks as you take heat out of them is going to change the aperture of the fracture, you might want to know what the initial fracture aperture is, because then it allows you to project how the permeability was changed as you withdraw heat from the reservoir. And so that's one reason that you might be interested to do that. And so we can define that this way. The rest doesn't matter. So I don't want to be too pedantic in explaining all this stuff. It's explained in a bit more detail there, but the bottom line is if you want to get the permeability of a fractured medium and you know that it has a number of fractures in it, then you can get it by this. Actually, this is the equation for one set of fractures. So if you had horizontal fractures in your reservoir and no cross-cutting fractures, this would be the magnitude. If you want the magnitude, if you have another set of, say, vertical fractures added to that, then you could just get the permeability by taking the permeability of one set. It's like a system, two systems in parallel, right? Not in series, but in parallel. So they're additive in terms of their volumetric flow rates. A second system is this one, and if you add these two together, you just get 2 over 12, which is 6. So you could also make the case that this should actually be not 12 over s, but 6 over spacing. So just a bit like what we did before with this idea of 32 and 96, right? This was just in, the porosity was divided among 3 tubes in 3 different directions. In this case, the flow rate is mediated between flow within the horizontal set of fractures and the vertical set of fractures, and additively there'll be double the amount of flow if the spacings in the apertures are the same. So that's that. I will go back to this just because, no, I don't need to. So rough magnitudes of permeabilities for a bunch of rocks. We probably shouldn't miss on that. I guess it always seems in strange units. So remember that we have permeability, viscosity is equal to hydraulic conductivity and density and gravity. Hydraulic conductivity, meters per second, permeability, meters squared per second. This is also, these are both the same. This requires that the fluid going through it has to be water at a relatively cold temperature. It's not so useful for to define, and it doesn't define the rock alone. Permeability defines the rock characteristics alone. And I guess 10 to the 2 centimeters equals 1 meter. So I suppose 10 to the 4 centimeters squared equals 1 meter squared. So I guess we have to multiply through by 10 to the 4 to change these. So this would be 10 to the minus 20 meters squared. This would be 10 to the minus, so 14, 12, 11, so 10 to the 11 would be 10 to the 15. And I only say this, so I hope I'm doing this right. So 10 to the 12 would be 10 to the six, right? And this. So yeah. So if this is, if I've done my conversions right, and this is really 10 to the minus 12 meters squared, then this is what's called 1 Darcy. This is 1 millidarcy, and 10 to the 18, which would be 1, 2, 3, 4. Am I off on this? 15. Are we missing a number here? 13, 14. 1, 2, 3. That'll be this one, right? Am I doing this right? Well, the right magnitudes of these are 10 to the minus 18 meters squared is equal to 1 microdarcy. Micro, 10 to the minus 6, 10 to the minus 3, and 1 for each of these. So hopefully, and those seem about the right. So some very tight rock that's no good for an EGS would be 10 to the minus 16. So we'll look in the second. If it's that lower permeability, then you have to bring it up perhaps 3 orders of magnitude, at least into this range, to make it a viable reservoir. This would be a fantastic reservoir, so long as you can pull the heat out of it. So basic ballpark numbers for those. Yeah, and you have some numbers there. Other versions of these Capri models for porous medias is the Cosini-Carman equation, taken out of Glassley. It doesn't really add to our discussion on this into what we've had already. So I'm skipping through this. And of course, you could make the case that for fractures, if you have 2 fluids flowing, they behave exactly the same way that you'd expect a porous medium to behave, and that you'd have relative permeability curves that you could use in the same way. So this nomograph perhaps is useful. It comes directly out of this relationship that permeability is given by b cubed over 12 times spacing. If you think about it also, of a porous medium, and if within this porous medium you had a, well, let me draw at the top. So if this was one repeating unit, where this was the aperture of a fracture, which is B, and the next fracture was just below it here, outside the medium, and this spacing between them was S, then you could write the porosity, which is equal to the volume of voids divided by the volume total, as being equal to, and if this length was just 1, just to make it easy, this would just be equal to B over S. Right? So the spacing The ratio of spacing to ratio of aperture to spacing, if you can measure it, is the porosity. And so you can make a nomogram, which is really just these two equations, which accounts for that. It gives you permeability as a function of porosity, which has to equal B over S, and as a function of different fracture widths. So I guess if you know that you have a fracture spacing of a meter, which would be this, 100 centimeters, and if you know that your fracture width is 0.1 of a centimeter, then this should be automatically 10 to the minus 2, I think. Doesn't look like it is, but it should be, right? So if it's 1,000, that's not a meter, that's, yeah, this is 10 meters, yeah, this is 10 meters. So then the porosity would be 0.1. It'd be 10 to the minus 3, I think. That doesn't look like it's right either. But you get the idea. And so if you have a fracture width and a spacing, then you have immediately a porosity, and you also have, going in this direction, a permeability. So you can do the same calculations just by putting the right numbers in here, but it's a nomograph that allows you to do that, and it varies between very high permeabilities, which are at the top, to very relatively low permeabilities, which are at the bottom. So this would be what we've called a millidarcy. This is a darcy, and 10 to the minus 18, which is off this figure, would be a microdarcy. So from what we said before, something in this range and above might be what would be useful to you to use in a reservoir, because if you can't get more fluid through it than would go through a very low permeability reservoir, you can't get enough mass output to be able to deal with it. So herein lies the rub. So this is a profile from the surface down to 35 kilometers in the crust. These are magnitudes of log permeability. So this is 10 to the minus 15 would be a millidarcy. 10 to the minus 18 would be a microdarcy. And so immediately you see that we're talking about maybe going down 4 kilometers. And so the idea is that the permeability really drops down as you go down the subsurface, because all the little fractures you have that are open and relatively compliant, as you get an overburden load increasing on them as you go further down, they close. And once they close, it can only go through the relatively impermeable matrix that is between the fractures, and that it's constrained to this. And so this means that if you're down at 4 kilometers and maybe you have permeability, which is this, still perhaps you have to do something with it to be able to get it into the range that is useful for you in terms of being able to recover fluids from a geothermal reservoir. Okay. So that's that. So we know exactly how to be able to take our system now to be able to calculate flow rates through this. It's just Darcy's law. Velocity, relative permeability, which is a function of saturation, times permeability, viscosity, pressure gradient. And we know immediately that if we multiply both sides by area, we get a volumetric flow rate. If we get a volumetric flow rate, then we know that the power out of our reservoir is going to be equal to the volumetric flow rate times its density, the mass flow rate, multiplied by specific heat capacity and whatever the difference in temperature between whatever depth it is and your disposal depth, your rejection of heat depth, the rejection of heat temperature at the surfaces. So we know at least how to do this. We can probably imagine that since this is a function of density, that the volumetric flow rate might be good if it's water, because this is 1,000 times higher for water than it is for steam, and I'm not sure that C changes very much. And so probably we're interested mainly in the water content out of the system. But typically, we might not be so interested in having a system which is given as a core sample, right? So what we've assumed here is that we would have an injection borehole, a recovery borehole, and we're putting water in. We're hoping to get the same volumetric flow rate of water out. Between these, we could represent it, I suppose, as something like this. And it wouldn't be very different from this. But of course, that's really not what the flow would look like. We know from 303 that if we look at the system of injecting and recovering in plan view, then we could imagine that we might get a flow line through here. Oops, I didn't do that. But the other flow lines might look a bit different. We talked about flow nets in this class. And so that's not really very close to our core system that we have here. So perhaps we have to look at some other ways to be able to characterize that. And so to be able to write Darcy's law in a more generic way that's useful to us, we need to jump into using some kind of conservation equation. It's pretty straightforward. You've seen this before. This is a velocity in or out multiplied by its change in space. So this is mass rate in minus mass rate out on this side. This is the accumulation term. So you can accumulate by either changing the volume of the bucket, the fluid in the bucket, or you can change the density of the fluid in it. So you can either pump it into a tire and keep the same volume but increase the density, pump it into an open bucket and change the volume but not the density. And we can define this volume as the total volume of our differential cube multiplied by porosity and multiplied through by the saturation, right? So we could substitute porosity, volume, and saturation in to replace this. We know what this is in terms of Darcy's law. This has to be a density to make the sides balance. Relative permeability between 0 and 1, 1 if it's one fluid. Permeability of the rock, we've just looked at what those are. Viscosity of the fluids that's flowing, and the pressure gradient. So we can substitute each of these in here. And if we do that, we get this. This is, let me use a color that's not on here. This is Darcy's law, as we had it before. This is both sides multiplied through by density. And this is the part, yeah, I don't care if you can reproduce this or not, but just understand that this is a balance between mass rate in and mass rate out, and this is net accumulation. We can split these terms up into derivatives of density and porosity separately, which is just what's doing here. Density times the rate of change of porosity with time. Porosity times the rate of change of density with time. And then we can do some things with it, which would be what? Multiply top and bottom through by dP, top and bottom through by dP, divide both sides through by density. I think I didn't mean to do that. This thing, this has little buttons on it, like a mouse on the side. And so now we can get rid of these, which is this. We can change this around to how porosity changes with pressure and how pressure changes with time instead of this, just rearranging it. We can also look at this. We can rearrange this in terms of changes in pressure with time instead of pressure with pressure. That's all we're doing. So we're taking what was this term here and we're splitting up the pressures. And we're splitting up the pressures. Again, it's unfortunate that density and pressure look very similar. Gamma versus pressure. And we haven't done anything with the other side except multiply both sides through by this. This goes to be 1. And the punchline, I guess, is this. We have a term which is Darcy's law. It's a second order differential instead of a first now. And this is mass rate in minus mass rate out still, but it represents an accumulation term. And the accumulation term includes the part which is due to the compressibility of the reservoir, the changing volume, if you like, of the tire as you pump it up, and the changing content of the pore space due to the compression of water. And so this would be the expansion of the reservoir inside your little representative element volume. And this would be the expansion of fluid within the pore space that's in there, because both can change their composition. So the change in volume with pressure of the reservoir is given by the Young's modulus, the 1 over Young's modulus of the reservoir. Typical Young's modulus for reservoirs are something like 10 GPa. GPa is 10 to the 9 pascals. Well, I guess it's written there. So 10 times 10 to the 9 pascals. And actually, surprisingly, I'm certain we mentioned it in 303, but the compressibility of water is huge. It's because it's the bulk compressibility. If you have water in a syringe and you push down on the end of it, it doesn't compress very much. In fact, it's only about a fifth as rigid as the reservoir. So it's pretty close to it. And so we can define both of those terms. And if we want to, we can write the equation and define particular conditions to it. We can also write it in terms of two different ways. We can write it in terms of pressure, which is, this is written in. So this is defined in terms of reservoir pressure. The issue with pressure relates to this idea that the swimming pool distribution is that we have to be a little bit careful with it, because if we have a hydrostatic gradient, that doesn't necessarily mean that there's any fluid flowing, because the gradient of this is cancelled by its variation in weight with height. And so the different way that petroleum and geothermal disciplines write this and groundwater hydrology write it is to write it, instead of being in pressure, write the equations in terms of head. And of course they're translatable between both of them. And one of the reasons we might want to translate it is that all the literature that talks about flow nets is written not in terms of pressures, but in terms of heads. And so we can use this relationship to be able to switch between them. The head of a reservoir is equal to the pressure head plus the elevation head. This is total head. And you've seen both of these terms certainly before. Don't care in this class about these relationships. We haven't talked about capillary pressures, so we don't need to visit them. So certainly you've seen you've seen all of these before. So the bottom line is that we could take this partial differential equation here, which we could write in x, y, and z by just expanding this term on the right-hand side into each of those orthogonal directions, if we wanted to. And if we look only at the x term, we end up with something like this. Mass accumulation in terms of the compressibility of the reservoir and the compressibility of water, which is what this is. This is compressibility of the fluid, compressibility of the reservoir. Or we could also write it in terms of specific storage. And so what we would do is we'd make, do I do the substitution later? Can't remember. Yeah, I don't. We can write it in terms of heads just by making substitutions with this for pressure and reworking these coefficients to be something different. So this now is hydraulic conductivity. And it conforms to, it's this parameter here. And it conforms to permeability. And this is referred to as specific storage. And it represents this term cast in a slightly different way. And we'll deal with it later on. So anyway, in the same way that we've done that, we've done this for a single phase in this particular case. So we've only talked about adding Darcy's law for a single phase. We could write it for two phases. and that's more complicated than we need to deal with. But in microcosm, what we can do is we can take the same continuity, conservation of mass equation. We could write it for both the water and the steam. So we end up with two equations. It's like two pipes in parallel. One has water in it, one has steam in it. They have different relative permeabilities as a result of that, and we can calculate them independently of them by flowing between the upstream and downstream pressures, which are the same in both two pipes. But because we have two equations, we have more than two unknowns. We have a saturation of water, we have an upstream pressure in the water, we have a saturation of steam, and we have a pressure gradient in the steam. So we have two equations but four unknowns. So we can close the set of equations by doing something, saying something to give us two more equations. We know that if we have two fluids, then the whole volume of the porous medium has to be taken up with either water and or steam. So the saturations must sum to 1. And we can define locally the pressure differential between them as being something called a capillary pressure. And a quick description of a capillary pressure would be, if you cast your minds back to thinking about two-phase fluids, which we dealt with in 303, which was if you stick a capillary in a fluid, then the water rises up in here because the water is trying to climb up the sides of the capillary tube. And so this curvature of the tube means that the atmospheric pressure here, which is also acting here and is also acting here, is not acting at this point here. The stress here in the pressure in the fluid is different from atmospheric pressure. And it's different because it's like the stress within a catenary of a suspension bridge is it's holding up the decking that's underneath, and therefore the pressure here would be in tension. So the difference between these two pressures is this capillary pressure, which we can use to close this system of equations. More complicated than we need to use here. Typically in geothermal reservoirs, you hope that permeability is high enough that this difference in pressure differential is small, and so we don't need to worry about it. So if we do that, we can write it for two phases, but we won't worry about that because we've already said that if we have two phases that are flowing, the steam that's flowing probably doesn't have very much heat content in it. So be it as it may that it's going through the system, we probably don't need to worry too much about the contribution to the thermal energy that comes out of the system. All right. So I made the case that we can define these equations in terms of heads and not pressures. If we do that, then the coefficients that describe these behaviors are now changed into hydraulic conductivity, specific storage, and head. Those terms are defined here. The specific storage is determined in terms of density and gravity of the fluids, multiplied by the compressibilities of the rock and the fluid. These are just as before. So the fluid would be, the rock would be 10 GPa Young's modulus. So compressibility alpha is just 1 over modulus, which is this term here. And likewise from fluid compressibility would be 1 divided by 2 GPa for the fluid. So our interest in doing this is now we can cast our behavior in terms of this system. So we can always move backwards and forwards between them. So the equation that you have above here is this in terms of hydraulic conductivity and storage. This is in the black here. If we divide both sides through by density and gravity, we can do that, of course, right? This term now here is equal to what we've called permeability of viscosity, right? We can make that substitution. In other words, this. And we end up with storage being also divided through by rho g. So it means that the rho g that we had here drops out. So this new value of storage is just this parameter divided by rho g, which is just this. So that's fine, right? And hopefully, since we know that pressure is equal to unit weight times h, we can also write this as head is equal to pressure divided by unit weight of the fluid. So if you do that for this, then we just end up with a term on both sides, which is 1 over gamma, which kind of cancels out. We don't need to worry about it. So it would just affect the units. So we could write it like this if we wanted to, because we're manipulating the head to convert it into pressure. But we don't need to do that. We can just perhaps ignore that. And so now what we can do is we can write our behavior in terms of these. The relative permeability is just mapping between 0 and 1. We can write the flow rate, again, as moving backwards and forwards between these in terms of pressure, which we've done before. And we can find out what the velocity would be. The units of this would be meters per second. If you multiply it by cross-sectional area of your tube, it would be meters cubed per second, volumetric flow rates. And we can define that. And I guess we're back to where we started off the day with. If we know what the volumetric flow rate is, we can calculate the power by knowing the fluids that are flowing and also the difference between reservoir temperature and the surface temperature. And all that we need to know is that within our reservoir, we're able to measure somehow what the relative saturation is, because that gives us this value, which is the relative permeability. And that's what we need to close the systems with. So it might seem kind of a circular task that we, first of all, describe behavior in terms of pressures, because it's much more rigorous. And if the pressures and temperatures change a lot, then we'd much rather work with permeabilities than we would with hydraulic conductivities. But the reason that we cast things in both forms is that when we look at this geometric flow that we talked about in terms of flow nets, and I guess it was up here, if we want to cast things in terms of flow that's not within this really very simple system here, flowing down a core, but have some kind of geometric effect, then we need to be able to have these partial differential equations. And actually, we can throw many of the terms away, but we need to define what those equations are. So that's what we will now kind of close out with. So this is the idea. So we can write our flow equation like this. If it's steady state, then that means that heads are not changing with time. That's not a bad approximation for a geothermal reservoir. And so I suppose you could imagine that if you had, we're doing okay for time. If we had our reservoir as we previously drew it, between an injection and a recovery borehole, and this was our surface. And say that we thought about what the pressure across our reservoir would be. Could be pressure, could be head. I know I'm overwriting everything. Could be pressure. I've already told you they're kind of not the same things. But so if it was head, if the initial head was the same, of course, if you take the same stratum at time 0, then you're looking just across the reservoir and this is the head. What would happen when you start pumping fluid in and pumping fluid out? You'd expect for this to be elevated in some magnitude, and this one to be depressed in some magnitude. And so typically what it would look like is that it would look kind of like this. Well, not very good. So this would be a cone of injection. This would be a cone of depression, as it would be called. The reservoir maybe is at some depth below this, so this is actually not within the reservoir, because this would imply that part of the reservoir is being desaturated, right? Because the fluid is going out of here. So let's say that this is the reservoir here. I know I'm drawing all over my own notes. But all I'm trying to make is the comment that the pressure differential between upstream and downstream is not going to be simply as we would have thought before, that it might look like might not look like the gradient here. Right? It's going to have curvature to it, and not only is it going to have curvature to it, if you look in plan view, it's going to have some topography. This is going to be a cone in plan view, if you looked at it, a hill, and this is a depression, a conical depression, and so it doesn't conform to that in any particular way. So what we can do is that when we start injecting, initially it'll look like this. As you keep on injecting, it will start looking like this. And at some stage, when it's reached equilibrium, which won't take very long, it might take a month, say, is it will start looking at the nexus of all of these, which is the bottom one. And then it won't change from that. So if that's the case, if it's not changing, then by definition, the change in head with time is 0. So you take a picture at 2 months, 3 months, 4 months, it always looks like this upper line here, and therefore this term on the left-hand side is 0, and this equation equals 0. So if we write this relationship out as a two-dimensional problem, then it would look something like hydraulic conductivity d2h dx squared plus d2h dy squared equals 0. Uniform permeability, so we don't care what this is. We can solve this equation by using flow nets, and we did in 303. I'm not sure we developed theory, but and we won't here either. But needless to say, we'll say that if you can describe the equation by that second order PDE, Laplace's equation is what it's called, then you can describe the flow regime as a series of flow lines, which would be the top line here, the black line, and these lines. These are streamlines and equipotentials. So the equipotentials are the ones that are going in this direction. So it goes from a high potential at this boundary. They're all uniform, all the same high potential, all the same low potential here, and it transits along a streamline. And a streamline which is the green here, defines a stream tube. So this would be a stream tube, just like in Bernoulli, essentially, stream tube. And the bottom line is, if we can define the boundary conditions of this system, so this would, you could think of this as just a square dam with water on the upstream side at some height, delta H above the height of this dam, and some water on the downstream side just level with the top of the dam. Then that's what this boundary condition would look like for the head drop across the dam. And the flow across the dam would conform to this. This would be a constant head boundary condition here. This would be another constant head boundary condition. They both have the same equipotential. This one would be a third of the way down, 2/3 of the way down, 3/3 of the way down towards this. And the stream tubes, streamlines would be given by these. Of course, there's an infinite number of these streamlines that you could draw in there. Right? These would all be streamlines. But the laws of drawing flow nets say that if you can draw a flow net that is roughly equiaxed and orthogonal, so the streamlines are perpendicular to the equipotentials, that each of the little cells that you end up getting are roughly equiaxed, same width and height, 1 to 1. and that it also satisfies the boundary conditions. So no flow boundary condition here. So no flow goes across this boundary, so it has to be a streamline. No flow goes across this boundary, so this has to be a streamline. And it also satisfies that these are equipotentials on the downstreams. So if you can do those three things, satisfy the boundary condition with your flow net, have the streamlines perpendicular to the flow line, to the equipotentials, and have the geometry that results from that is roughly equiaxed in terms of the cells, then this equation directly describes the flow through the system. And so this says that the number of flow tubes that you have, the number of drops that you have from upstream to downstream, multiplied by the hydraulic conductivity, which is K, and by the head drop. Gives you the flow rate. So this would be equal to meters per second times meters. So meters squared per second. These are just numbers, so they are numbers. And so the units would be meters squared per second, and it would be per meter into the page. So the meter cubed would come from the extra meters. And so if we do that, we can calculate immediately the value of the flow rate. If we want to do it in terms of hydraulic conductivities, then that's fine. But we might also want to do it in terms of permeabilities. And so what we could do, I suppose, is we could multiply top and bottom. Well, the equation below this just does that. Multiply top and bottom by rho g by 1. This now becomes permeability. This now becomes permeability. This is delta H, and so this delta H rho g, this term here, would be delta P, right? From upstream to downstream. So it's just a different way of doing it. I guess that's written here. And so it's very, very easy to do. So you have a geothermal field. We have a spacing, say this might be, for an EGS project, this might be 0.5 kilometer between two wells, 500 meters. So you start off with these two wells, and then you draw in your first streamline. You know that there has to be a streamline that goes from your injection point to your recovery point. You add a second streamline on top of that, and you do it as an artist to get these different stream tubes. And you already have that written down here. And then to accommodate these, you now start to draw equipotentials. Has to be an equipotential that goes down the middle. Has to be an equipotential that goes around here. These are actually circles, not centered on here, but they go out to some broad distance out here, so they're not concentric. And likewise here. And you start filling it in. This flow line, by the way, here goes out here to plus infinity, and then round the back of the universe, and back here from minus infinity over here, which is how that works. And these kind of do the same things as well. These would just be those. And then you start to apply this equation here. So to calculate the flow out of here, if we had, I don't know, if we had 11 MPa as the pressure here, if we had 10 MPa as the pressure in this well, and this was, I guess we actually don't need to know this distance at all, right? Then we could calculate the flow rate from this as being flow rate is equal to number of flow channels, number of drops, times permeability times delta P. And so for those terms, this would be 11 minus 10 MPa. delta P, right, between the injection and recovery. Whatever permeability we want, we said that we want milli-Darcy at least, so it'd be 10 to the minus 15 meters squared. We can choose. And number of flow tubes would be how many? This would be, we've got to start somewhere. So this would be 1. I guess I've done it already. So they're counted here. So this would be, go from here. So this would be 1. Yes, this is stream tube 1, stream tube 2, stream tube 3, stream tube 4. This is just an arrow for this. Stream tube 5, 6, 7, and 8. So a number of flow tubes would be 8. The number of drops would be going from half an hour to the witching hour. This would be 1 drop, 2 drops, 3 drops, 4. So this would be 4. And so you'd end up with a volumetric flow rate equal to the number of stream tubes over 2. It looks like this is roughly of the order of magnitude of 2. This is of the order of magnitude of 1 megapascal. This is the order of 10 to the 15, minus 15 meters squared. How did viscosity get left out of here? Oh yeah, by definition, K over rho G is viscosity, right? And so this has viscosity in here. I'll do it in red. And I think the viscosity of water at 20 centigrade is something like 10 to the minus 3 Pascal seconds. Water at 200, I think it drops by an order of magnitude, is something like 10 to the minus 4 Pascal seconds. You can check it. I'm not absolutely sure, but it's of that order. And so that allows you to be able to calculate everything here. We have viscosity, we have pressure drop, we have permeability. This geometric number doesn't change very much. It's really quite insensitive. If the wells were closer together, I think it would be the same geometry, right? It's kind of, the geometry would just shrink. And this, you'd have to multiply by depth into the page. So if the wells were 1,000 meters within the reservoir, then this depth would be the depth within the reservoir. Yep, go ahead.
What was the number of drops again?
The number of drops. So this is the first one. This is the first equipotential here with the black one on it. This is the second equipotential. This is the third, and then you're at the other well. So it's 1, 2, 3, 4. Right? It's like this. In this case, it's this would be 1 equipotential. This would be another. So going from here, this is 0. So you go 1, 2, 3. Right? That's physically what it is. And so you have a pretty robust way of calculating it. I mean, you can do it in 2 seconds. Obviously, I take longer to do it because I'm not very clever. But once you have this, you have a volumetric flow rate. Volumetric flow rate multiplied by density gives you a mass flow rate. Specific heat capacity, change in temperature, gives you a pretty robust way, but a very straightforward way in being able to calculate your power output from a reservoir. And that's our goal, was here to be able to figure out how much fluid can you get across your reservoir. Because if you know what the rate of which you can get fluid out, we said that you need to make from a well something like 100 kilograms a second at about, I don't know, say 200 degrees centigrade to get 5 megawatts of electricity out of it. And so you need to generate enough revenue to be able to pay off the $5 or $10 million you cost to put in the well. So 100 kilograms per second is a tenth of a cubic meter in terms of volumetric flow rate. 100 liters a second, in other words. And so that's the question that's there. What you can't tell is that if we do know what this is, we've got a pretty good estimate of this. If we know it's water that's coming out, we know what the specific heat capacity is. I guess the other big unknown is whether the fluid that you're injecting cold and hoping to take out hot has enough residence time and heat surface area in the reservoir that it picks up and robs all the heat from the rock to be able to take it out. And so that is really the unknown. So you can't necessarily assume that this is going to be 100 or 200 degrees centigrade, because it might come out. You can imagine if you're pushing water through a pipe, that it goes through quickly, that there's no real conductive heat contact area with this pipe and the fluid, that you put water in cold, and even though the outside of the pipe is very hot, it'll come out at the other end still cold. And that's really what we're talking about. And I should stop talking.